How do we solve a system of linear equations? Solution of linear algebraic equations might sound abstract at first, but they are everywhere. From predicting the stresses inside a trucis to optimizing routes for navigation systems, even to the algorithms behind computer graphics and AI. For better understanding, let's explore a specific example. Imagine you are a civil or mechanical engineer designing a triangular truss and making sure it will not collapse. Several external forces are acting on the truss, as you can see on the screen. In addition, tension and compression forces develop inside the members to balance these external loads. Our goal is to determine these internal forces, as well as any unknown external forces, so that the system remains in static equilibrium. Let's start by listing the unknowns. There are 6 in total, which means we need 6 independent equations to solve for them. To form these equations, we rely on a fundamental principle. In a static system, the net force in both the x and y directions must be 0 at every joint. This condition applies to each point of the truss. Since we know the applied forces at joints A, B, and C, we can analyze these joints separately to derive the equations. For example, at joint A, we can write 2 balance equations, one in the x direction and one in the y direction. In the x direction, we have the force F3 plus the horizontal component of F1, and their sum must be 0. In the y direction, we have F sub I plus the vertical component of F1, which must also equal 0. By applying the same procedure at joints B and C, we obtain all 6 equations we need. Now, instead of solving them one by one, which will be tedious, it is much more efficient to express them as a system of linear algebraic equations. Let's first clear the page. Good. Now, we will build our matrix system, starting with zeros that will be gradually replaced with values. We begin by filling the unknown vector. Then, we insert the coefficients from each equation into the matrix, step by step. For the first equation, we place the multipliers of F3 and F1. Repeating this process for the remaining equations, we obtain the complete matrix form. So far, so good. But we now face the same big question. How do we actually solve this system of equations? This time, however, we have a much clearer understanding of the structure of the problem. With this understanding, in the video series, we will explore methods for solving linear algebraic equations step by step, starting from the fundamentals and gradually moving toward the powerful techniques widely used in engineering and science today. So, let's dive in and begin the journey. Numerical methods are divided into 3 categories mainly. First, direct methods. Second, lower-upper decomposition methods. Lastly, iterative methods. In this video, we will focus on the direct methods, and in the upcoming videos, we will explore the rest of them. So, let's explore the first method. These methods aim to find the solution within a finite number of steps. The first technique is Cramer's rule. This method is actually more suitable for systems with a small number of equations, and we will understand the reason later. Now, let's examine this technique with an example. Suppose we have an equation like Ax equals b, where A is a 3 by 3 matrix. There is an exact procedure to find each unknown in the vector 1 by 1. For example, the first unknown can be expressed as a fraction of 2 determinants, where D is the determinant of matrix A, and the numerator is obtained from D by replacing the first column of coefficients with the B vector. As you can guess, we can find each unknown in 3 steps, and in this manner, the remaining 2 unknowns are obtained as follows. Note that while the second column is replaced by the B vector for the second unknown, the third column is replaced by the B vector for the third unknown. Up to this point, everything seems fine, but it is important to mention that if the number of equations is larger than 3, this method becomes inefficient, since we need to find every unknown one by one. Also, calculating the determinants of large systems of equations is a tedious and time-consuming task. At this point, we can propose a new method which handles the solution of large number of equations relatively better. Its name is naive Gauss elimination. We can expand the understanding of this method by analyzing it in 2 steps. In the first step, named forward elimination, we manipulate the equations with the other equations in the system in order to eliminate one of the unknowns, and we get an upper triangular form. At first, it may be hard to perceive, so let's visualize it through an augmented matrix, which is plotted as on the screen at T, the first stage. We eliminate these two coefficients by subtracting or adding a multiplier of the first equation, which is denoted as our 1. While the multiplier is a sub 2, 1 over a sub 1, 1 for second equation, a sub 3, 1 over a sub 1, 1 for the third equation. In addition, for this stage, the first equation is called pivot equation, and a sub 1, 1 is called pivot element, since they are the decider of the multipliers. By implementing these two computations, we obtain the updated form of the matrix. I know matrix seems a little bit messy, so before continuing, let's simplify it a little bit, and later we will put the values back. After the simplification, at the second stage, we eliminate this coefficient by using the multiplier of the second equation, where the multiplier is d over a. For this stage, pivot equation is the second one, and pivot element is a. After implementing this computation also, eventually we are able to obtain the final triangular form. Now, it is time to jump into the second step, back substitution. In this step, we will simply solve the updated equations. And I want to point out that at the last equation, there is only one unknown, which is x sub 3, and we can directly find this unknown value by simply solving for it. Perfect! Now our remaining task is quite simple. We will only put this known value to the upper equations and find the other unknowns respectively. Let's find the remaining ones rapidly. Hopefully, I believe that we successfully understand the two-step process of the naive Gauss elimination. In order to enhance this understanding, let's get deeper into the methodology with an example. Suppose we solve a system of equations which composed 3 equations as given. Start the process by putting this system of equation onto an augmented matrix. Perfect. Now, we can go on with the first step, which is forward elimination by eliminating the coefficients below the pivot element. To do that, we may add 3 over 2 times first equation to the second equation and add 1 times first equation to the third equation. After implementing these two computations on the matrix, the remaining coefficient to eliminate is the coefficient below the new pivot element in column 2. For this elimination, we should subtract 4 times second equation from the third equation. By also implementing this final computation, as we see, we obtain the upper triangular form of the matrix hopefully. Then we can directly jump into the second step, back substitution. Through the last equation of the system, we can easily obtain that x sub 3 is minus 1. By using this known value, from the second equation, we obtain another relation. By using the relation, we simply get that x sub 2 is equal to 3. Lastly, by solving the first equation of the system for x sub 1, we find this unknown is equal to 2. Actually, this example quite simple since we did not encounter any nasty situation. However, as every numerical methods, naive Gaussian elimination has several drawbacks that must be considered when writing a computer code. So, I wanted to devote some time to these drawbacks and their partial solutions with proper visualizations. The first thing to mention is the possibility of division by zero error. This error arises when the pivot element of the column is actually 0. To visualize this error, let's look at the example given. As you see, pivot element of the first column is 0, and the problem will rise in error during the elimination of the coefficients below the pivot element. The remedy to this error is simply interchanging the pivot equation with another equation, such as the third equation that has no 0 element. This procedure is named as pivoting. So, our computer program should check the pivot element whether it is 0 or not to prevent division by 0 error. Second drawback to discover is round-off errors. Now, suppose we have a system of equations like the one plotted as an augmented matrix. We want to apply forward elimination, So we subtract 1/3 of the first equation from the second equation for elimination of the coefficient below the pivot element. In the final form of the matrix, we get a coefficient whose significant figure representation is entirely up to us. To see the difference, let's solve the equation with 2 and 6 significant figures separately. Since the computation of the unknowns is quite simple, we will give the exact results of the unknowns. For 2 significant figures, we find that x sub 1 is equal to 0.89 and correspondingly x sub 2 is equal to 0.16. However, for 6 significant figures, we find that x sub 1 is equal to 0.894737, and in addition to that, x sub 2 is equal to 0.157895. As we can observe, there is a discrepancy between the results. 0.004737 for x sub 1 and 0.00211 for x sub 2. At first, this differences may seem small, but as the number of equations increases, the discrepancy will also grow due to error propagation. To compensate for this error, we can store as many significant figures as possible in our computer code. Thirdly, we can talk about one of the most important aspects, ill-conditioned systems. This is a system condition, and to explain it, first, we should make a distinction between well-conditioned systems and ill-conditioned systems. In literature, well-conditioned systems are the ones where a small change in a coefficient has not much effect on the result. On the contrary, for the ill-conditioned systems, a small change in the coefficients results in drastic changes in the solution. Let's visualize this distinction with graphical solution. Seemingly, 2 systems of equations are assigned for each condition, and the representation of the equations on the coordinate system are like those which are plotted. The solution of the 2 equations are the point where 2 lines are intersecting. With this information, if we look at the graph of the well-conditioned system, we are able to detect the intersection point easily. Therefore, even though we make a very small changes in the coefficients, this will not make a considerable change in the results. However, this is not the case for an ill-conditioned system. For instance, let's look at the example given for it. We cannot detect the intersection point precisely since they are almost parallel to each other, and even we move a line by changing coefficients, we have to face with a huge change in the solution. These changes in coefficients may occur unintentionally like round-off error, as we mentioned before. Now, we need to answer a crucial question. How can we understand our equation is well or ill-conditioned beforehand? Actually, we're able to characterize this question with a system of 2 equations. Let's think of 2 equations of systems as we did before, and put them into the form of y equals to slope times x plus intercept. We learned that if the lines are almost parallel, which means they have the almost same slope, they converge to ill-condition. With this information, we can reach to this conclusion for an ill-conditioned system. Also, let's put the expressions to the same side. At this point, it's crucial to recall that this final expression is determinant of 2 by 2 matrix. This tells us an important reality that as the determinant goes to 0, the system converges to ill-condition. So, can we conclude that we can differentiate the systems whether well or ill-conditioned by computing their determinant value? The answer is yes, but we must consider that we are able to scale the determinant of a system by scaling an equation. For this condition, it is good practice to scale the system to their largest value 1 while comparing their condition. In addition, we can expand this idea for systems that has more than 2 equations. Before going to the end, I want to give a good news that most of the engineering problems are naturally well-conditioned, so the system condition will not be a nasty problem for our implementations. In conclusion, we have discovered the world of the direct methods by going through the literature and examples of several techniques in the upcoming videos. We will explore the lower-upper decomposition and iterative methods respectively. Thank you for watching and following along with this explanation. Remember to subscribe to the channel and turn on notifications so that you won't miss any of our future videos. See you in the next video.